Imagine this. You take a circle, maybe put, say, 4 or 5 points around the edge. Now, here's a little challenge. How many ways can you draw lines chords between those points? But with a key rule, none of the lines can cross each other. Sounds simple, right? But this geometric puzzle leads us straight into today's deep dive. The really fascinating Motzkin numbers. These are named after Theodore Motzkin, who, well, first pinned them down mathematically. They specifically count the ways to draw those non-intersecting chords we talked about. And interestingly, you don't actually have to use every single point. Some can just sit there.
Right, that flexibility is key. And what's really striking is how these numbers just sort of emerge from this visual problem, but then spread out across mathematics. The sequence itself, it starts 1, then 1 again, then 2, 4, 9, 2, 1, and so on. And these aren't just abstract figures. They have real fundamental applications in geometry, certainly, but also combinatorics, even number theory. They're quite foundational.
Okay, let's make that concrete. You mentioned the sequence starts 1, 1, 2, 4, 9. So for 4 points on that circle, there are exactly 9 ways to draw the chords without crossing. Is that right?
Precisely 9 ways, yeah.
And then add just one more point, up to 5 points.
And it jumps to 21 ways.
Wow, okay. That escalates quickly. It feels surprisingly rich for such a, well, basic setup. What gives them that power beyond just counting drawings?
That's where the deeper structure comes in. The visual part is just, the hook. Mathematically, these Motzkin numbers follow specific patterns, recurrence relations, meaning you can predict the next number from the ones before it. It's like a built-in growth rule.
Mm-hmm.
And even more elegantly, you can express them using things like binomial coefficients, from Pascal's triangle.
Oh, right.
And also using Catalan numbers, which are, well, famous in their own right for counting non-crossing things. So it shows this deep connection, how different mathematical ideas are really intertwined. That's where the real significance lies, finding those unifying patterns.
Okay, so we have the visual side, the connections to other sequences. But there are more surprises packed into these numbers themselves, aren't there? I read something that was, frankly, astonishing. Like regular integers, there are Motzkin primes.
That's correct, yes.
Numbers in the sequence that are also prime numbers. Examples like 2, okay, and 127. But then 15,511, and get this, a massive one, 953 quadrillion, 467 trillion, and change. Just huge.
Mm-hmm. Quite something.
Does that primality tell us something extra fundamental, or is it more of a, fascinating curiosity?
It's certainly fascinating and underlines that these numbers, even though they come from counting things, also have these inherent number theoretic properties, like other major sequences do.
Right.
But shifting gears a bit, there's another whole way to look at them through combinatorics. Motzkin numbers also count something called Motzkin paths.
Motzkin paths. Okay, what are those?
Imagine a grid, like graph paper, just the top right quadrant. You start at the corner, 0, 0. A Motzkin path takes you to nen 0 back to the horizontal axis in exactly in steps. And each step can only be diagonally upright, straight right, or diagonally down right.
Okay.
And this is the crucial part, you can never dip below that horizontal axis, the Y0 line.
Ah, I see. So like a walk with specific moves, but you can't go underground, so to speak.
Exactly. Like a tightrope walker who can step up, down, or straight, but never fall off the rope downwards. The number of ways to take such a walk of length is the nth Motzkin number.
That's remarkably different from drawing chords in a circle.
It is, yet it's the same sequence counting both.
So tying this together, we have chords, paths, prime properties. What's the big picture here? I think Donaghey and Shapiro found something like 14 different interpretations.
At least, yes.
Yeah.
Back in 1977, they enumerated 13 distinct mathematical objects or problems counted by the Motzkin number m and n. It's quite versatile.
Incredible. So we kicked off this deep dive with a simple geometry puzzle, drawing lines in a circle, and it led us to the Motzkin numbers, a sequence weaving through different mathematical fields, holding prime secrets, and even describing paths on a grid.
It really highlights how a single, elegant mathematical idea can pop up and describe such a wide variety of phenomena. It's a beautiful example of the unity in mathematics.
Absolutely. It makes you wonder, doesn't it? What unexpected connections might you, listening right now, find between different things you know, just by looking closely for patterns and underlying structures? Something to think about. Until next time on The Deep Dive.